Jai Hind, welcome to the course Network Analysis and Synthesis, and today we are going to discuss about the network synthesis. So, learning objectives of this lecture is first, what is network synthesis? So, if you remember during the course of network analysis, we discussed what is network analysis and what is network synthesis. So, a network is given and there is input and there is output. When the network is excited by a input and the problem of determination of output or response is known as network analysis. So, what is network analysis? Network analysis deals with the determination of response when the network is excited by a predetermined input. By the same way, when the input and output are known, okay, and you are required to design and fabricate a network, that problem is known as network synthesis. So, we will discuss in detail what is network synthesis, then what are the tools required to synthesize a network, that is known as elements of realizability, and they are Woodbridge polynomial and PRF, positive real functions. So, before a network can be realized, if it is PRF or it is Woodbridge polynomial. So, later on we will discuss what is Woodbridge polynomial, what are the properties or what are the conditions required for a function to be a Woodbridge polynomial and positive real functions. So, we will discuss in detail in this for these two topics, Woodbridge polynomial and PRF. Then we also discuss the methodology. How will synthesize a network, what are the techniques that are being used to synthesize a network, that will be discussed in methodology of network synthesis. And then in the last that is synthesis of LC, RC and RL. Basically this is two elements network synthesis, or you can say the one port having two elements either LC, RC or RL using Foster and Cole first and second forms. So, these are the special types of network synthesis we will discuss in detail in the last. Okay. Then we can see here, just reminding, this is the network and it is excited by input and we get the output. So, input and output are known and you are required to design and fabricate a network. That problem is network synthesis. So, if you summarize, what are the tools required for synthesizing a network when input and output are known? So, they are called element of realizability, that is to determine whether the network function could be realized as a physical passive network. So, and they are, first is the Woodbridge polynomial. So, what is Woodbridge polynomials? It is a denominator polynomial of network function satisfying certain conditions, and other one is the PRF. So, what is PRF? It represents physically realizable driving point emittance functions. So, if you remember network function, say this is F, suppose this is Fs is Bm s to the power m Bm minus 1 s to the power m minus 1 plus say B1s plus B0. Okay. Then we have the denominator polynomial An s to the power n minus 1, An minus 1 s to the power n minus 1 plus say this is A1s plus A0. So, it is a given network function, and this Bm and Bm minus 1, these coefficients are nothing but these are the circuit components, or you can say the network components. So, how will this synthesize, that we will discuss later on. First I am just here defining what is Woodbridge polynomials. So, this is the denominator polynomial of a network function. If it is satisfying certain conditions, then it becomes a Woodbridge polynomial. So, first we will discuss what is Woodbridge polynomial, what are its properties, and how we will carry out the test for a given function whether it is Woodbridge polynomial or not. So what is the definition of Hurwitz polynomial? A polynomial is said to be Hurwitz if the following conditions are satisfied. That is, QS is real when S is real. So where we get the QS, we will get QS here. This is your Fs. It is the ratio of say PS upon QS. So this is your QS. Okay. So straight away we just take the denominator polynomial of a network function and check whether QS is real for real S. What is real S? If you remember, S is equal to nothing but it is sigma plus j omega. This is the real part of that is the complex frequency. S is the complex frequency, and this is the imaginary part, or you can say the imaginary frequency. So this is the real part. So for when the S is sigma, QS is also real. Okay. Then the roots of QS is equal to 0 have real parts which are either 0 or negative. So what does it mean? It means if we, this is the polynomial, if we equate QS is equal to 0, it becomes equation. So which are either 0 or negative, it means it should lie. Suppose you draw the S plane. Okay, this is your real S, that is your say sigma, and this is your j omega. So roots real part either 0 or negative will lie this side. Okay. Then what are its properties? If the Hurwitz polynomial can be written as, so it is nothing but it is, you can see it is the denominator polynomial of a network function we have taken. These are the coefficient an minus 1 up to the a1, a0. These coefficients must be positive. This is the first property is a0, a1 up to the an, they must be positive. However, we have the corollary to this property that between the highest order terms in S and lowest order terms in S, none of the coefficient may be 0 unless until the given polynomial is either odd or even. Okay. This means that all the coefficients must not be 0 if the polynomial is neither odd nor 0. So this is the corollary of the property first. Then the second property is both the even and odd parts of Hurwitz polynomial have roots on the j omega axis. This is your j omega axis. Then this is very important, just to carry out the whether the given polynomial is Hurwitz or not. What we do, we just carry out continued fraction expansion of ratio of even to odd parts or odd to even parts of a Hurwitz polynomial gives all positive quotients terms. Okay. What does it mean? It means polynomial is given, separate the even parts and odd parts and try to carry out the division, that is the continued fraction expansion, and if all the quotients are positive, then the given polynomial is Hurwitz polynomial. So testing point of view, this is very important. Third property. Then this is explained here. So this is the basically we have separate, suppose MS is the even and NS is odd or odd to even, depending upon the which function higher order is either odd or even. If the higher order is even, then we divide even to odd. If the higher order is odd, then we divide to odd to even. So these are the we carry out the continued fraction expansion. These are the positive quotients. Okay. If all alpha 1, alpha 2, alpha 3 up to alpha n, if all are positive, then the given polynomial is Hurwitz polynomials. This is, you can see. Clear? Now suppose if you are carrying out the continued fraction expansion and after 1 or 2 division the remainder becomes 0. Okay. So what we will do, it means this QS has a factor WS. So what we will do, just separate, we just separate Ws and Qs from the Qs and try to find whether this Ws and Qs are Hurwitz polynomial or not. So that is, we have to carry out testing for Hurwitz polynomial separately for Ws and Q1s, just to check whether the Qs is Hurwitz or not. Clear? Okay. So property 4 is clear. It means if if the after one or two divisions, if the Qs remainder of the Qs becomes 0, then your continued expansion stops there. What we will do, just we separate the Ws and Q1s from the Qs and carry out the testing for the Hurwitz polynomial Ws and Q1s separately. If the ratio of the fifth is, if the ratio of polynomials Qs and its derivatives give a continued fraction expansion with all positive quotients, then Qs is Hurwitz polynomial. Why this property number 5th is required? Why it is required? Sometimes suppose the given polynomial is either odd or even. So it is very difficult to carry out the continued fraction expansion. So what we will do, if the function is either even, take the first derivative will be the odd, and then we proceed for the continued fraction expansion. So these are the some properties of Hurwitz polynomial, or these are the guidelines to check whether the given polynomial is Hurwitz or not. Suppose this problem is given, Qs is equal to s to the power 4 sq 5s square plus 3s plus 4, whether it is Hurwitz polynomial or not. So just check. So I can write here now come to the positive real function. So what is positive real function? A rational function fs is positive real if the following conditions are satisfied. Fs is real for real s, that is f sigma is real. The first condition is fs should be the real. The second is real part of fs should be greater than or equal to 0 for real parts of s greater than or equal to 0. Then what are the properties? Properties are, if fs is positive real, then 1 by s is also PRF. What does it mean? It means if the impedance function is positive real, then admittance function is also a positive real. Driving point impedance function is PRF, then driving point admittance function is also PRF. The second property is the sum of PRF is positive real. However, difference of two PRF is not necessarily a PRF. Then poles and zeros of PRF cannot have positive real parts. That is, they cannot lie on the right hand side of the S plane. This is the third property. The fourth is only simple poles of Fs with real positive residues can exist on the j omega axis. So what is j omega axis? Already explained. Just you have to draw the S plane. This is your sigma and this is your j omega. The poles and zeros of a PRF are real and occur in conjugate pairs. The highest power of the numerator and denominator polynomials may differ by unity at most. So difference between the highest order and lowest order, highest order of the numerator and denominator must differ by 1. the lowest power of the numerator and denominator polynomials may differ by unity. So, in the difference of highest of the numerator and denominator polynomial may differ by unity at the most, or it may be equal. The lowest power may differ by unity at the most. The eighth property, it is basically the about the necessary and sufficient conditions for a given function, network function to be a positive reals. So, numerical point of view, we just go for this property number 8. So, what are this? Fs must have a no poles on the right half of S plane. How will ensure that this is satisfying? So, for this, what you have to do? You have to just go for the testing of the Fourier polynomial. Then Fs may have only simple poles on the j omega axis with the real and positive residues. How will ensure? Just carry out the partial fraction expansion and try to find the constants k1, k2, kn. If they are real and positive, then condition number 8b is satisfying. Then the third is, which is the most important, the real part of fj omega is greater than or equal to 0 for all omega. So, these are the three necessary and sufficient conditions for a given function to be a positive real. Then how will carry out the testing? Okay. So, for testing, just for condition 8a, check the denominator polynomial is Hurwitz. Okay. Then for the condition 8b, expand the given function, carry out the partial fraction expansion and find the coefficients constants k1, k2, kn. If they are real and positive, then condition 8b is satisfying. In order to test for the third condition, for the positive realness, what we will do? We just take the real part of the Fs. So, how we will do it? Just suppose this is the given function, Fs is the network function having the numerator polynomial in S to the denominator polynomial in S. So, what we will do? We just separate the even parts and odd parts of the numerator polynomial as well as denominator polynomials. So, this is m1s plus n1s, m2s plus n2s. So, here m1s is even part, n1s is the odd part of the numerator polynomial, whereas m2s and m2s is the even part of the denominator polynomial and n2s is the odd part of the denominator polynomial. So, just separate m1s plus n1s, m2s plus n2s. Now, what we will do? Just multiply the conjugate of this denominator, m2s minus n2s. Okay. So, we get this m1s, m2s minus m1s, n2s, m2 square s minus n2 square s plus. So, look at here, m1 is a even and m2 is even. So, product of two even function is also even, n1 is odd and n2 is odd. So, product of two odd functions is even. So, this is the even part of the this Fs and this is the odd part of the Fs. So, we can separate, this is the even part here and this is the odd part. So, to check the condition 8c, we have to check the even part of the Fs. So, take the even part, real because real f j omega is the even. Okay. So, this is the real part and we have to check this condition, real part of f j omega greater than or equal to 0 for all omega. So, what we will do? We separate the real part of the and the odd the real part and imaginary part of the Fs and take the real part and we just go for this. So, I will do is this. So, denominator of this this is always positive, denominator of this even part is always positive. So what we have to check? We have to check the numerator, which is m1 j omega, m2 j omega minus n1 j omega, n2 j omega for greater than or equal to 0. Okay. So this is the alternate definition of PRF. These are required just to if the numerical is the function is given and you are required to just to go for the testing. So we have to do this 3 ABC already explained. So what is the explanation of the A part? A part requires determine whether the denominator polynomial of S is Woodbridge. Okay. It can be readily tested through the continued fraction expansion. Tested by taking the partial fraction expansion of the Fs, and if the all the constants k1, k2, kn all are the real and positive, then it is satisfying the condition 2. So to test the third condition, this is the real f j omega is greater than or equal to 0 for all omega. So all this we explained. So this this slide is just recapitulating what we do for testing a PRF. Then there are some special cases. Suppose the Fs is given in this format, s plus a, s square plus bs plus c, where a, b, c all are constant. If the given Fs is in this format, straight away we can check whether this is a PRF or not. How will do it? So check whether a, b, c they are greater than or equal to 0 or not, and second is b should be greater than or equal to a. So if these two conditions are satisfied, then the function given in this format is a PRF. Then another case, suppose the Fs is given in this format, s square a1s plus a0, s square plus b1s plus b0, where a0, a1, b0, b1 all are real and positive constants. So if the function in this format, so what we will do, just take this a0 plus b0 minus a1 plus b1, take the whole square, minus 4a0 b0 should be less than or equal to 0, and second a1 b1 equal to the square root of a0 minus square root of the b0 and take the whole square. If these conditions are satisfied, then we can check whether the given function Fs in this format is positive, real or not. Then there are some examples just here given. You can note down or you can check positive realness for these functions. I can do here for the first one. How we will carry out the exercise to check the whether the given function is positive realness or not. So say this is Fs is I am writing here, Fs is s square plus 10s plus 4 divided by s plus 2. Okay. So here what we will do, just put s is equal to j omega. Okay. So f j omega equal to j omega square plus 10 j omega plus 4 divided by j omega plus 2. Okay. So, what we will do, just to separate the real and imaginary, what we will do, just multiply the conjugate of the denominator. So, this can be written as, so j square omega square plus 10 j omega plus 4 divided by say 2 plus j omega 2 minus j omega 2 plus 2 minus j omega. Okay. So, what we will do, just take if we separate the real part, then the real part is coming like this, real f j omega, it is coming 8 omega square plus 8 divided by omega square plus 4. This is the real part. Okay. Okay. So, this is the real f j omega, which is 8 omega square plus 8, okay, 8 omega square plus 8 divided by omega square plus 4. So, this is always greater than or equal to 0, this condition satisfied, taking the any value of omega. If you be taking the negative value of omega, then it is a square, so it will coming the positive. So, this way we can check whether the given your function is PRF or not. So, there are 3 conditions: go for the Woolrich polynomial, test, check the poles residuals are real or positive, and third one is the real part of f j omega should be greater than or equal to 0 for all omega, Okay, this way we can check the positive realness of a given function. Now come to the methodology. How will synthesize a given function? Okay, if the function is given, and how will get the network. So, what are the method that are being used to just synthesize a network if the fs is given. So, network function is, this is the network function, this is the numerator polynomial in S to the denominator polynomial in S. So, this is basically, this is the input output relationship, all the coefficients Bm, Bm minus 1, B1 and B0, these are the circuit parameters, or you can say the network parameters. You have to remove, you have to decompose and get the elements. So, how will do? So, there are 4 methods, and we can use either of the following or their combination. So, we do the removal of pole at infinity, removal of pole at origin, removal of conjugate imaginary poles, and removal of a constant. So, how will check whether there is a pole at infinity? Okay, pole at origin we can check. If this is A0 is missing, if A0 is absent from the denominator polynomial, certainly there is a pole at origin, but how will check the pole at infinity? In the normal case, there's poles and zeros must be equal in a network functions. Okay. If there is deficiency of a pole or a 0 vice versa, then that pole or 0 must be at infinity. Okay. So, how will check there is a pole at infinity? Look at the degree of the numerator polynomial. If it is lower than the numerator, means n is less than m, it means there is a pole at infinity. Then removal of pole at origin, we can check if the a0 is absent, means there is a pole at origin. Then how will check whether there is a conjugate imaginary poles or not, we can check, and the removal of constant. So, these are the methods to just carry out the network synthesis or decompose this network function fs. So, take one by one. So, removal of pole at infinity, if the fs has pole at infinity, s is equal to infinity, then m minus n is equal to 1. So, there is a deficiency 1, it means one pole is lying at infinity. So, check, just look at the numerator, degree of the numerator and the degree of the denominator. If m minus n is 1. So, how will remove it? Just divide the numerator polynomial by denominator polynomial. Straightway we can get this fs is equal to hs ns upon ds in this format. Okay. So, this hs, if this fs is, suppose this fs is a driving point impedance function, if it is impedance, then this is a impedance. Okay. So, this is impedance, means what it should be, hs. So, it should be a inductor. So, we can get, if we are removing a one pole at infinity, we are getting one inductor if the function is a driving point impedance, and this is the value of the inductor Bm upon An. So, H is equal to Bm upon An is the value of the inductor. So, if the impedance, then S can be realized as the inductor of value L is equal to H, which is Bm upon An. So, by removing one pole from the network function, we are just separating one inductor. So, this can be the symmetric. So, we have removed one inductor, and this is your remaining F2s. Then the further exercise will be carried out, checking whether there is a pole at infinity, 0 at the infinity, or the complex conjugate. So, this way we can proceed. So, this is the first step. Suppose if your driving point network function is admittance, it is driving point admittance function. Okay. Then removal of pole at infinity will give a capacitor of value this. So, if you are removing pole at infinity, and if the given function is driving point admittance, we are removing a capacitor from the function. Okay. So, then this is your y1s and this is your y2s. So, further exercise will be carried out just to decompose this y2s depending upon the what is the degree of the numerator and what is the degree of the denominator. So, we can see that if we are removing a pole at infinity, we are getting either inductor or a capacitor. If the function is driving point impedance, we get the inductor. If the driving point admittance, we get the capacitor. Now, the second method is removal of pole at origin. Okay. So, how will check it? That is, the constant a0 must be 0. In that case, we can have a pole at origin. We can see here the a0 is missing from the denominator polynomial, and then we have the pole at origin. So, what we will do, just look at here, we have arranged the polynomials in ascending order and we can carry out the division, first division. Okay. So, arrange the polynomials in the ascending order and the divide, we get this term k0 by s, or this is the one way to just remove the pole, or the another one, take the partial fraction. Okay. So, that will be the long procedure. Better we arrange the polynomial in the ascending order and divide numerator by the denominator, we get the k0 by s term. Suppose this fs is a driving point impedance function, then this is a capacitor. This k0 by s will give a basically this will give a capacitive. So, this k0 is, so what is the value of the capacitor? It will be 1 by k0. If we write in the numerator 1 by k0, so the value of the capacitor, we know that if we convert the capacitor in S domain, it will be 1 by SC. So, the factor of the S is here 1 by k0. So, when we are removing a pole at origin, it means we are eliminating capacitor from the function. Okay. And then we carry out the exercise. Suppose C is equal to 1 by k0. So, this is the, so when you are removing a pole at origin, we are just removing or separating the capacitor. Okay. And then the further exercise will be carried out just to decompose Z2S. Similarly, if Fs is an admittance function, then k0 by s represents the inductor of value 1 by k0. So, if we remember, if we convert inductor in this domain, so it is SL. Okay. So, what is SL? So, this is, so 1 by Ls is the admittance. So, this way we can take the value of inductor. Okay. So, what we have seen, we have seen that if you are removing a pole at origin and if the function is impedance, we are separating the capacitor. If your function is admittance, we are separating the inductor. So, this is the schematic 1 by k inductor, and then the further we can decompose Y2S. Okay. Now, come to the removal of conjugate imaginary poles. Fs is given ns upon, just we have ds is equal to 0, then we have to find the poles. So, we have the one complex pole, that is 1 s plus j omega into s minus j omega. So, we take the partial fraction and we just finally we get this 2k1s upon s1 square plus omega n square plus f2s. Okay. How will get the value of k1 n omega 1s? So, just for this, just take this is a LC. Okay. Just take the impedance of this function, convert it into S domain. So, SL into 1 by SC, SL plus 1 by SC. So, ZLS is 1 by C into S square plus 1 by LC. Okay. So, when the L and C, they are connected in parallel and we are finding the equivalent impedance, we are getting in this format. Okay. Now, try to compare this ZL with this one, because this is the impedance. So, this will be impedance. Okay. So, 1 by C is equal to 2k1, 1 by C is equal to 2k1. So, C is equal to 1 by 2k1. Okay. So, this way we have the value of the constant, we have carried out the partial fraction expansion and we have determined the value of k1. Omega 1 is nothing but it is the frequency. So, k1 and omega 1 given, and with the help of this the two variables k1 and omega, we can determine the L and C. So, the for C it is 1 by 2 k1, and this omega 1 square is nothing but it is 1 by LC. Just look at this one. So, just to make it clear, draw the LC in parallel, find the equivalent impedance and compare with this. So, L1 C1 is 1 by omega, so L1. So, this is C1 and this is L1. So, this way we can find the value of LC. So, we have seen that when we are removing a conjugate imaginary poles from the network function, we are separating one LC tank. Okay. So, this is the result of removal of one complex poles. Okay. And then the Z2, then we look at what is the scene, whether there is a pole at infinity, pole at origin, what is, then we can carry out. Then Fs is an admittance, then what we will do, just write the L and C in series, L and series in series. So, Zs is equal to Sl plus 1 by Sc, and take the Ys. Okay, clear? L and C, they are connected in series. So, this is Zs, and then this is Ys, just invert it, we get the admittance. Now, compare with these two, 2k1s upon S square plus omega n square of this. So, what we can see, 1 by L is equal to 2k1 or 1 by L1 is 2k1. So, by this we can get the value of your inductor. So, 1 by L1 is equal to 2k1. So, L1 is 1 this way. Now, compare 1 by LC is omega n square, so C1. So, if the admittance, then we can get the value of L and C in this way. Okay. So, this is the result. This is the value of L and C in series, and then Y2S. So, further we can, depending upon the what is the scene, then we can carry out the other methods, removal of pole at infinity 0. Now, come to the removal of a constant. This is very important. So, we remove the minimum value of this k minimum at some frequency. The gist of this technique is, without divide the numerator by the denominator without disturbing the PR property. PR property should not be disturbed. Suppose we divide the numerator by, suppose the degree is same, m and n both are same, okay, and divide. So, we get some constant, but the remainder becomes negative. Okay. So, what we will do? It means we are disturbing the PR property. Okay. Okay. So, PR property is disturbed. So, keeping in mind not disturbing the PR property, we carry out the fourth one. Now, there is one problem, synthesize the network. This is the impedance function. So, we look here, we can see here, this is S square plus 2s plus 6, S square plus 3s. So, but here this is, there is a pole at origin. So, pole at origin means removal pole at origin. So, what we will do? Just arrange the polynomials in ascending order. Arrange the polynomial in the ascending order, and then take the division. This 3s square plus 3s plus s square, divide in this, we get 2 by s. So, we have removed the pole at origin, we have get this one 2 by s plus s square divided by s square plus 3s. Okay. So if this is the impedance, so this is also impedance. So 2 by s, what is it, what it should be? It should be a capacitor of half farad. Okay. 2s, s plus 1 by z1s plus z2s. Now this is the impedance, so it is a capacity of capacitance half farad. Now look at the z2s. So z2s is s by s plus 3. So what we will do, just invert it. Just invert it. S plus 3 by s. So just divide 1 plus 3 by s. We have this is the admittance. So this is admittance. It is a conductance, and 3 by s. So this is the admittance. This is admittance. This is also admittance. So we are this is the inductor. This is the admittance. So the final circuit will be like this. So this is the your capacitor. Zs is equal to 2 by s plus s by s plus 3, z1s plus z2s, s by s plus 3, and y2s is just inverting it. So 1 plus 3 by s. So this is the decomposition of Fs. We are getting the capacitor of capacitance half farad. Then we have the conductance, or you can say the 1 mho or 1 ohm, both are same. So and then we have the inductors. So that given function has been decomposed into the RLC network. Okay. Then there are some special formats. So previously we discussed the generalized, how it decompose in the form of the RLC. Here the Foster and Courts, they have given the synthesis of a network of a given function in forms of two elements, either RL, RC or LC. Okay. So they have given the Foster forms and the Court forms. So what is Foster forms? Basically there are two forms of Foster. One is the series network realization and one is the parallel network realization. So if the function is impedance, we go for the Foster first. If the function is admittance, we go for the Foster second. Okay. Here what we are going, here we are carrying out we are just developing a ladder network. So how will we get the ladder network? We just carry out the continued fraction expansion. How will do it? If we are carrying out the continued fraction expansion about infinity, we are getting the core first form. If we are carrying out the continued fraction expansion about origin, we are getting the core second form. So these are the basically one port, two element simple network synthesis. So we'll discuss these two forms, Foster first and Foster second, of RL, RC and LC networks in detail in the next lecture. Thank you. Jai Hind.